everyone. In this session we'll be taking a look at 3.2, which is polynomial functions of higher degree. First I want to start talking about the graphs of functions according to their degree. And well, first off, we've seen graphs of linear functions, we've seen graphs of quadratic functions. These are both polynomials of degree 1 and degree 2 respectively. We'll take a look at cubics, which are degree 3, but then we'll also take a look at polynomials of even higher degree. But for right now, let's just talk about their graphs. And recall that a linear function has a graph that is either positive sloped or negatively sloped. And really what's going on here is that this has to do with the leading coefficient of the polynomial. So if you recall, a polynomial is of the form basically ax to some power plus bx to the one lower power plus cx to the next lower power and so on. So in the case of linear polynomials, it would be ax plus b or mx plus b. So we like to think of it as m, but in reality, let's just call it a for the leading coefficient. So a is what is called the leading coefficient. Very often, by the way, I like to label leading coefficient and abbreviate that by LC for leading coefficient. So here, this is when the leading coefficient is positive, versus here below is where the leading coefficient is negative for linear functions. For quadratic, we saw something very similar. For quadratic functions, their graphs were parabolas. It was a facing up parabola when the leading coefficient was positive, and facing down when the leading coefficient was negative. Cubics will look kind of similar as well. They will look something like this. So notice, it increases. So it goes off to infinity as x goes to infinity. So it opens up as x goes to the right and it opens down as x goes to the left, basically. And when the leading coefficient is negative, though, opposed to positive, it's just the same image but reversed. So there's a few important things here. The biggest important thing I want to talk about that we'll emphasize a lot in this section are the number of zeros. Remember that 0 of a function corresponds to its x-intercepts, and x-intercepts are the amount of times that it hits the x-axis. Well, those are the number of x-intercepts anyways. So the number of zeros, of course, for quadratics, we saw that it's possible you have 0, 1, or 2, but we're going to talk about the largest possible amount of zeros for a polynomial. So here, for linear, there's only one 0. There's only one x-intercept. For quadratic, the most is 2. For cubic, the most you can have is 3. Now, it is possible that you can have 0, 1, 2, or 3 zeros for or x-intercepts for the graph of a cubic function, but again, we're talking about the most amount, and the most amount is 3. So now we're going to take a look at what happens for even higher degree beyond 3, and we'll kind of see what the graph looks like. Basically, we're going to be counting these humps or bumps or lumps or whatever you want to call them. Here there's 1, here there's 2. I wonder what it's going to be for higher degree. Let's take a look. Okay, so now for higher degree polynomials that are bigger than 3, degrees larger than 3 that is, we have the quartic, quintic, and sextic polynomials, so degree 4, 5, and 6 respectively. Now their graphs look kind of like what you'd imagine them as being based on what we saw, based on the number of humps from quadratic and cubic polynomials. So quartic will have 3 humps like this. So you always start off, well, you always want to go up towards infinity as x goes to the right. That's basically what we're kind of forced to do here when the leading coefficient is positive. When the leading coefficient is negative, we're forced to go down as you go to the right. And we're forced to have a maximum of 1 less than the degree number of humps. So in this case, the degree is 4. So we'll have a total of 4 minus 1, which is 3 number of humps. So there's 1, 2, 3, that's it, so it has to go back down. If it went up, then there'd be 1 more hump, and it wouldn't be quartic, it'd be quintic. So with that being said, quintic will look like this, having 4 humps. When the leading coefficient is negative, however, the image is reflected like this, vertically. So sextic would be this parabola looking thing, but it has a bunch of humps in between instead of just one in between, or like none in between like the parabola. In in the case of quadratic functions. Perfect. So you can kind of see the trend here. When you have a even degree polynomial function, it either opens up or opens down in both directions, and there's a bunch of humps in between possibly. Okay. Now, as far as the number of zeros go, remember those are x-intercepts. There should be a maximum 4, and here they are, 1, 2, 3, 4 for quartic. For quintic, there should be 5, and for sexic, there should be 6 maximum. Now, I need to emphasize on something that's kind of important here. These are exaggerations as far as the polynomial equations are concerned. If you graph x to the 4th on your own, which is technically a quartic polynomial, it'll look very much like x to the 2nd. It'll be just a parabola. In that case, there are 0 humps in between. And there may not be, but the maximum there can be in between are 3 like this, if that makes sense. So you can try playing around with graphing different things in your calculator just to see what it'll look like. But in any event, these are the extreme cases for these degrees of polynomials. Oh, by the way, I want to emphasize something that I didn't really say last time in the last screen that I should have. When I described this general polynomial here, I didn't say this, but it should go on and on and on. And the last term will be a constant. It'll have no x's. So the power of x in each term decreases to 0. So just as an example, for the quartic, the general quartic polynomial will look like this, algebraically. It'll be f of x equals ax to the 4th plus bx to the 3rd plus cx to the 2nd plus dx, and then finally plus e. And then you can see how it'll look for the other cases as well. The power of x, as you see, starts with the degree and then decreases until you have no x's in your constant term. So now we're going to take a look at some examples where we actually find the zeros of a certain polynomial equation of higher degree, and even go beyond that and try our best to graph it. So let's see that. So in these two examples here, we can see that these are definitely polynomials. Also, we can see the degrees. The highest power here is 3, highest power here is 4. So this will be a cubic, this will be a quartic polynomial. Now, the leading coefficient here is negative, so it'll go down as you go to the right, and this is positive, so this indeed goes up as you go to the right. So just to get an idea of what the graph looks like, I may erase this later, but the graph will look something like this in this case. Actually, it's negative, so it's flipped. So it actually looks like that image flipped like this. There we go, in this case. And here, this will look something like this, just to get an idea. But now, as far as exactly what it looks like, let's find the x-intercepts and I guess y-intercepts as well. But the x-intercepts are really what we care about, and remember these correspond to the zeros. So how you find the zeros of a function is just by setting it equal to 0 and solving for x. And in doing that, we get negative x cubed plus 4x is equal to 0. And how do we solve this equation? Well, we factor. So what do they have in common? You can pull out, let's do this. Let's pull out x squared, and we'll have negative x plus 4 on the inside equals 0. So you can always factor completely and then set each factor equal to 0 using the zero factor property, as we've seen before. When x squared is equal to 0, that means x is just 0. Okay. Also, the only other one we have here is, well, when you set negative x plus 4 equal to 0, if you add x to the other side, you get x is equal to positive 4. So notice, here, as we've said before with cubics, you would have at most 3 zeros, but here we only have 2, so something funny is happening. And let me try to explain a few things. But before I do that, let's, I guess, find the y-intercept. It's not too difficult to do that. So the y-intercept is just plugging in 0, and that'll be the point 0, comma, well, when you plug in 0, you get 0. So we have a y-intercept, and these are our x-intercepts. So to graph this, we have a y-intercept at y equals 0, and an x-intercept at x equals 0. And remember, the graph is going to go down like this. And we also have an x-intercept at 4. So we're forced to pass through these 2 points, only these 2 points on the x-axis, and it has to have that shape we agreed on earlier. So no matter how you do it, there's no other way for this to work unless, well, I guess there's a certain case where, so it has to look something like this. But there is a certain case where it passes through this point at 0, and then I guess it would bounce up at 4 and then jump back down. I'm going to talk more about this bouncing up opposed to passing through situation in the next screen, but the biggest takeaway that I can say right now is that this has to do with the fact that 0 occurs as a solution twice because it came from x squared being equal to 0. So technically, if x squared is 0, that means either x is 0 or x is 0. So you get 2 hits of this solution. This is what we have seen before, known as multiplicity 2. So how multiplicity will affect the graph basically is either it just straight passes through if it's an odd multiplicity, or bounces if it is an even multiplicity. But I'll summarize that in the next screen. But in any event, the graph looks something like this, and you can graph this on your own, and you can see that. Good. So now for this one, we'll do something similar. We want to set it equal to 0 and factor the non-zero side, so I'll just start factoring. Notice they have 2x squared in common. So we do indeed have a multiplicity here because there's a power of this factor. Here, this is not a power of a factor because this can actually be factored further. It can be factored as a difference of squares, x minus 1 times x plus 1. Just like that. So these are for the x-intercepts. And using the zero factor property, what do we get? We get either x is 0, and that's multiplicity 2. Again, because it comes from x squared being 0. If x minus 1 is 0, then you have x is equal to positive 1. If x plus 1 is equal to 0, you have x is equal to negative 1. Okay? And just like we had above, the y-intercept is also 0, 0, because when you plug x equals 0 in, you get 0 as a result. Okay, so now how must this graph specifically look? Well, let's try to plot our points that we have to pass through, namely our intercepts that we were discussing here. Well, we have to pass through 1 and negative 1. And we have to pass through 0. Because these are on the x-axis, because these are our x-intercepts. Okay. What else? Oh, well, the y-intercept is also 0. That's fine. Okay, so at x equals 0, there's an intercept. Well, the multiplicity is 2 at that intercept. So it'll just touch it. Also, the leading coefficient is positive, so it goes up in both directions. So with all of that in mind, the graph has to look something like this. With all that in mind, it has to pass through those points that we've emphasized on as the intercepts, and it has to bounce up to 0 and just touch it. It can't pass through because it has a even multiplicity. Alright, so now just a little bit of information about the zeros of a polynomial function. So first let me say the following are equivalent. The following 4 things are equivalent. If x equals a is a 0 of f of x, where f of x is a polynomial, of course, then of course that means x equals a is a solution to the polynomial equation f of x equals 0. This is just vocabulary, that's what 0 means. The next thing I think is fairly important, and this is kind of what we saw from the last example. We saw that factoring helped us find the zeros. So let me say this. X minus a is a factor of f of x. So if x equals a is a solution or a 0, then x minus that number is a factor. Very, very important. Secondly here, or I guess fourthly here, a comma 0 is an x-intercept of the graph, and we saw that as well. Zeros corresponded to x-intercepts. Good. And now I want to talk a little bit about repeated zeros, which is what we saw to do with the multiplicity and how it affected the graph of the function. So a factor x minus a to the k yields a repeated zero x equals a of what is called multiplicity k. So multiplicity is again how many times it appears as a factor, basically the largest power of that factor that's present as a factorization of the polynomial. And 2 things I have to say here, what I've already kind of mentioned, but at least here it's written down for us. If k is odd, then the graph crosses the x-axis at x equals a, But if k is even, then it doesn't just cross it, it actually only just touches it. So just to kind of explain what that looks like, for 1, it'll look something like this at x equals a. It just touches, or just doesn't just touch, but actually crosses through at x equals a, where this is the x-axis, of course. Opposed to the second one, where the multiplicity is even, here it just touches at x equals a. Just like that. Okay, so now we're going to see some more examples where we actually find the zeros again, and let's see those right now. Alright, so these are the last examples I'm going to do for this section. They're not as crazy as the ones we saw previously. In fact, these are ones we could have seen on 3.1. These are just, well, they're just quadratic functions. But let's see if we can keep in mind what we've just learned. Let's factor them as much as we can. So factoring this, we get x minus 6, x plus 6. So that means by the zero factor property, we have x-intercepts of negative 6 and positive 6. The y-intercept will be 0, comma what? Well, if you plug in 0, you just get negative 36, the constant term. Okay. So, right. The leading coefficient is positive, so this will be a facing up parabola. And it'll have to pass through the x-axis at negative 6 and positive 6, and the y-axis at negative 36. So this, of course, will not be to scale, but the parabola will look something like this. Passing through 6, imagine that passes through 6. Looks a little better, I guess. Perfect. Okay, so that was it for this one. I didn't even say what we're supposed to do here, but I wanted to find the zeros and then sketch the graph. Here, to find the zeros, well, again, we need to factor this. What two numbers multiply to positive 9 and add to negative 6? It's negative 3 and negative 3. So notice x minus 3 times x minus 3 is just the same as what? It's just the same as x minus 3 quantity squared, because you have a repeat of that factor, meaning you'll have a repeat of the 0. So here we have only x is equal to 3, but it has multiplicity 2, because the power is 0. If the power was 3, it'd have multiplicity 3, but again, it's 2. And remember what we also saw from the previous screen, when the multiplicity is odd, it passes through, but when it's even like it is here, it'll just touch it at 3. And also we can find the y-intercept by plugging in 0. When x is equal to 0, we just get the constant term 9. So plotting these on the xy plane, we have y equals 9, let's say that's over here, and y equals 3, let's suppose that's over here. Now it has to pass through these 2 points, but remember, well, also it'll be a facing up parabola because it's positive in front of x squared. It's a facing up parabola, and it has to just touch 3. Otherwise, if it didn't just touch 3 and pass through at 3, since it's a parabola, it'd have to open back up, so then it would have another x-intercept beyond 3, and it doesn't. This is the only solution. So we end up getting this. Perfect. So again, these are kind of not super crazy examples, but they're examples nonetheless. And hopefully it helps us reinforce what we learned from 3.1 and makes it even easier to graph. And I think it certainly does. So try to go back and look at these subtleties we saw. We'll be seeing them in the next few sections for chapter 3, so keep those in mind as well. I'll see you in the next videos for 3.3 and 3.4. It's going to be fun. See you then. Thanks for watching.